Hello, today our topic is entropy and the second law of thermodynamics. Now, ideal gas law tells us that PV equal to nRT. This will have an extensive use throughout this section. PV equal to nRT, this is the ideal gas equation. এটা আমরা অনেকবার ইউজ করব এই সেকশনে. Let me recall you the first law of thermodynamics, which tells us that change in the internal energy is equal to the amount of heat going into the system plus dW is the amount of work done to the system. So there is a conversion of heat and work, and energy is a measure of heat plus work. So we can say heat is work and work is heat. Now let's consider a gas in a container. Suppose I am having this container filled up with a gas. There is a piston on top of the container, and we can apply pressure P on the piston. The piston can move upwards and downwards. If we push this piston downward, that is, we apply pressure like this, like in the downward direction. So dl is the amount of movement of the piston downward. If we want to calculate the work done by you on this gas, we have this equation. We know pressure P equal to force divided by area. So force on the piston is equal to pressure times area. Now work is done on the system by definition is dW equal to F dot dl. Now F is pressure times area, force is pressure times area, dot dl. Now what is A dot dl? A dot dl is area of the piston, dl is the amount of displacement of the piston. So this is the volume by which the gas is compressed. So we can write A dot dl as dV, that is a change in the volume of the gas. Now let me introduce a negative sign into this equation, that is dW equal to minus PdV, which accounts for the fact that if we do more work on the piston, the volume of the gas decreases more. So if we increase W, work done on the gas, its volume decreases more. That is, if we apply more pressure on this piston, this gas will be more compressed, and that accounts for the negative sign in the dW equal to PdV equation. So we can write this as dW equal to minus PdV. As work increases, volume of the gas decreases, and if the volume of the gas does not change, that means dV equal to 0. So it's quite evident from this equation that dW, that is the work done, is also equal to 0. So we rewrite the first law of thermodynamics, which is du equal to dq plus dW, and dW is here minus PdV, and this equation will also have extensive use throughout the section. Now let's look into internal energy of the gas. Now internal energy, we can write it as a function of temperature and volume. You can ask me that why it is not a temperature of function of both temperature, volume and pressure. I mean a function of all the three quantities. Now virtue of this equation, PV equal to nRT, which is the ideal gas equation, if we define temperature and volume, then P is automatically defined by this equation. So we won't write it as U as a function of temperature, volume and P. We will take it as U is a function of only temperature and volume. So if du is a function of temperature and volume, so the total derivative of du is equal to partial derivative of U with respect to temperature when volume is constant times dt. Volume is constant, it is written as suffix outside the bracket, plus partial derivative with respect to the volume when temperature is constant into dV. Now if the volume of the gas does not change, so dV equal to 0. If dV equal to 0, this term will vanish and du will be only this du will be only del u del T at constant volume times dt. And if volume does not change, that means dV equal to 0. So, from the first law of thermodynamics, we can rewrite this, that du is equal to nothing but dq only. So, du equal to dq if the volume is constant. So, come to the equation for dW, total derivative of the internal energy, which is equal to du equal to partial derivative of the internal energy with respect to temperature for constant volume times dt. This is defined as heat capacity at constant volume, which we will write it as Cv. Cv is the heat capacity at constant volume and is defined by this relation. So, we can write from the first law of thermodynamics. Now, as V is constant, so dV equal to 0. So, du equal to dq only, and that is equal to Cv dt from this equation. Now, let us define another quantity which we will call enthalpy, not entropy, this is enthalpy. Enthalpy is defined as U plus pressure times volume, internal energy plus pressure times volume. Now, let us write H enthalpy as a function of temperature and pressure. From the first law of thermodynamics, we have du equal to heat going into the system plus work done on the system, and we know that dW equal to minus PdV. So, du equal to dq minus PdV. So, we can write this as d, just changing sign of this side state change. So, du plus PdV equal to dq. Now, taking this d out, we simply write this equation, that d of U plus pressure times volume, which is equal to dq, and this is by definition H. So, dH equal to dq. Now, similarly, like internal energy, which is a function of temperature and volume, we are writing enthalpy as function of temperature and pressure, and for the partial derivative, the total derivative of the enthalpy in terms of the partial derivatives, we can write as partial derivative of enthalpy with respect to temperature at constant pressure times dt plus partial derivative of enthalpy with respect to pressure at constant temperature times dP, and this is by virtue of this equation dH equal to dQ. But for constant pressure, this term vanishes, and so what remains is dH equal to, this is 0, this term is equal to 0, and this is equal to dQ. Now, we define this